Let's look at ladders. Ladders consist of a beam that you've propped up against a wall in the ground. In our problems, we will never have friction on our wall, and we have to have friction on the ground, or the beam is going to fall out and begin to rotate. Let's diagram the forces on the ladder. We have a frictionless wall. So we have a normal force coming out of the wall, hitting the surface of the ladder. I'm going to call that F normal wall. Then I have a normal force coming up from the ground. I call that F normal ground. We know that there's friction on the ground, and the friction is opposing the motion of the ladder. The ladder's trying to slide this way, so friction is going the other way. Then we have a gravitational force on the center of mass of the ladder. And later on we might put more things on the ladder. Maybe we'll put something here. Maybe we'll put something here. But for right now, we just have the one object, or the ladder itself, and the gravitational force of the ladder itself. I'm going to call that FG ladder. Why isn't the ladder spinning? The ladder isn't spinning because the sum of the torques around whatever point I pick to be my pivots are equal to 0. Now, where should I pick my pivot? I'm going to pick my pivot to be the most complicated part of the setup, because every force that goes through the pivot, does not create a torque on that object. So this force is going through the pivot. So this force does not exert a torque on the ladder. This force does not exert a torque on the ladder because it goes through the pivot. So if I choose the pivot here, the only forces that are going to make torques on this ladder is the blue one and the green one. So together they have to sum up to be 0. So let me go ahead and do that. Why did I make this positive? Because this torque would cause this beam to rotate counterclockwise. Counterclockwise is a positive torque by convention. This torque would cause the beam to rotate clockwise. Clockwise is a negative torque by convention. So obviously these torques have to be equal. I want to fill in what these are equal to. Just a reminder, torque by definition is either the perpendicular force times the distance that that force is from the pivot, because only perpendicular forces cause torques, cause rotation. Or, mathematically, torque can be observed as the force times the perpendicular distance. So extend the line of action of the force until it is perpendicular to the pivot and find that distance. So that is what we're going to do. Looking up here, here's the direction of the force. That force is located here. Is that force perpendicular over here? No. So I'm going to extend that force out until it is making a right angle with the pivot. That occurs right here. And this is my perpendicular distance. Now, I'm going to use trig to figure out what that distance is. How far away is this force from this pivot in a perpendicular line? We need to know an angle. Sometimes we know this angle. Other times we know this angle. It depends on the problem. If I want this side and I know this angle right here, then I'm going to use cosine. If I want this side right here and I know this angle, well then this angle is equal to that angle, and I'm going to use sine. So you need to look at the trig to decide what is the best expression in this case for our perpendicular. I'm going to pretend that the problem gave me this angle right here, in which case, what am I going to use? I'm going to use sine. Filling in Fn, R, where's that come from? Well, that was the length of the bar, because that is where Fn is located. I wanted this perpendicular length, so it becomes R sine of theta. Now I'm going to do the same thing with the torque from the ladder. That's right here. I look at this force, and I decide how far is this force located from the pivot in a perpendicular way. So I extend this line of action down, and I find out what this perpendicular distance is. Well, I need to know this length in order to find this length if I know the angle theta, and from before we had decided that this was the angle we were going to pretend the problem gave us. So if I know this length, okay, and I know this angle and this length, I can use cosine to find this length. I want to point out again, if I had been given the angle here, right, if we had known this angle right in here, then this angle would be that angle, and I would use sine. So you have to look at the problem and see which angles are given you. Now you're going to simply solve for whatever is unknown. Maybe you're solving for theta, maybe you're solving for the length of the bar, maybe you're solving for the weight of the ladder or the normal force on the wall. But at this point, you're going to be able to solve for some numbers. At this point, I'd like to point out that if this whole length here is what we were calling R, the length of the beam, the center of mass of the ladder is at 1/2 that length. So this length is now 1/2 R cosine theta, because the hypotenuse is R only 1/2 R. Okay, so that's where this 1/2 R comes from. In the first example, we were asked to solve for the normal force from the wall. So we can see that we can cross out R and rearrange. I went ahead and did that. I rearranged, and in this particular case we also know theta. We know in this particular problem that I believe theta was 70 degrees. We also knew in this particular case the weight of the ladder. The ladder was 50 newtons. The ladder was 50 newtons. So solving for Fn gave us 9.1 newtons. At this point they ask us to solve for the remaining unknown forces, but they're really very simple. We have one horizontal force and we have one horizontal force. Together they have to sum to 0. So we've just found this force. It has to equal that force. We know this force. It's the only vertical force downward. It must be balanced by the only vertical force upward. We know this force, so we know that force. Sometimes we're asked, will this ladder actually stay like this? Or is this just an idea? And if I really set it up at that particular angle, it might slide out. Well, in order to do that, we would simply figure out what is the maximum frictional force possible. The maximum frictional force possible for this setup is, like in any setup, mu Fn. So you look for what Fn is, you multiply it by mu, and you find out what is the maximum static frictional force possible. If the frictional force possible, max, is greater than what you've got, then it's going to stay standing. In this particular problem, we'd already figured out that the normal force on the wall, which is equal to the frictional force, was 9.1. It told us we had a mu of 0.2, and we already knew that Fn was equal to Fg. We knew from the beginning that Fg was equal to 50. So we know that the max static friction possible is 10 newtons. We're only needing 9.1, so this will stay standing up.